Good morning. Welcome to Krishna's classroom. In this talk, we continue with our exploration of MF and M and analyze the structure of M, which is going to be the sigma algebra that is induced by lambda. Okay, so we have to show that it is indeed a sigma algebra. So that's our task. So we just recall whatever the definition of MF and M. So we shall write here. So we have X EX mu to start with. Then we have MF defined as E subset of X with the property that mu of E is finite and mu of E equal to, that means E can be approximated from within by compact sets. That's what we want to see. So mu E is equal to supremum of mu of K contained in E, K compact. So the suprema is taken over all K, which is compact, and inside E. So this is what we have as MF. Now, having got MF, we can define M, which we shall put down here. M as the set of all E contained in X with the property that E intersection K belongs to MF. K compact so we have these definitions now. What we have already shown is that prove that MF mu on MF is countable additive. That's one of the results that we have proved earlier. Okay. We also proved that, so this is probably, let's write this as step 4. Step 5. We proved that if E belongs to MF and epsilon is any positive number or a given positive number, then there exists a compact set K contained in contained in E and an open set V containing E such that mu of V minus K. Remember, K is contained in V is less than. So, given epsilon, you can find a pair K and V where K is open. So, it's like this. So, E is given. This is E. Then you have got a compact set here, some K, this is your K. Then you have a open set such that for this portion mu is equal to mu of V minus K is less than 0. That's the result. This we have proved in step 5. So these are some estimates that are useful in exploring the structure of M. Okay. So now we further analyze the structure of MF, and we in the next step we have the following. If A belongs to MF and B belongs to MF, then A minus B, A minus B, A union B, and so what you have is A is B, this is A, this is B. Then A minus B is this one. This is in A union B is the whole thing. This is A union B. And this is A intersection B. They are all in parallel. Okay. So these three pieces that you have and the whole which is given by the union of A and B, they are all elements of MF. This is again a step towards proving that M is a sigma algebra, as we shall see soon. But we shall prove this first. This is just simple manipulation on the operations on sets. Okay, so we'll do this. If epsilon is positive, by step 5, there exists Ki and Vi, B equal to 1 and 2, such that these two properties are satisfied. K1 plus or K1 contains A and K2 K2 and mu of Vi minus Ki is fine. Sorry, is less than x. So this is something that we observe. So we have two sets. So you have got a V1 and K1 here, V2 and K2 here, and this kind of properties are satisfied. Now, note that A minus B is contained in B1 minus K2, which is contained in B1 minus K1 union K1 minus V2 union V2 minus K2. So V1 minus A minus B is contained in V1 minus K2. That is easy to see. And then this can be split up, or this is a breakup that you have for this. Therefore, you see that mu of, see, you are using subadditivity. Mu of A minus B this is just subadditivity that you are using, less than or equal to mu of V1 minus K1 plus mu of K1 minus V2 plus mu of V2 minus K2, which is equal to, which is less than epsilon plus mu of K1 minus V2 plus epsilon. I think I will just take off from here. You can retain this for some more time. And then what we get immediately from this is, note that K1 minus K1 is compact, V2 is open. So this is the intersection of K1 with V2 complement. Okay. Is compact. And is a subset of now you see, this is closed and a part of K1. K1 is compact, therefore this is also compact. That's the argument. And is a subset of A minus. That's very easy to see. Which implies A minus B satisfies the condition see, this is a compact subset of A minus B. Condition that mu of of A minus B equal to supremum of, this is of course mu k contained in K compact. And that implies A minus B so if A and B are in MF, then A minus B is in. What next? We have to work on A union B and A intersection. Now, A union B is equal to A minus B union B. By step 4, see these are disjoint. This is a disjoint breakup of that. A minus B is in MF, B is also in MF. Therefore, we get, see you have additivity and therefore we have A union B is the belongs to MF being disjoint union of and that follows from step 4. Okay. So we take A intersection. A intersection B is equal to A minus A minus. Now you see that A minus B, A belongs to MF, by what we have already put in the beginning. It follows that A intersection B A minus B in MF and A is in MF. So A minus A set which is in MF is again in F. That is that. So we have proved this result completely. So what we observe is that MF has, if A and B belongs to MF, then A union B, A intersection B, A minus B, they are all elements of, or it is closed under union, intersection and differences. Needless to say that B minus A is also in MF. Okay. So when you have these components, now this is this equation. You have got A, this is A, this is B. Now A union B is the whole thing. Then A minus B is this portion. A intersection B is this portion. And B minus A is this portion. So A union B, A minus B, B minus A intersection B. They are all in MF. That's a nice step. Now we go to the next step. Step 7. Okay. Step 7 is that recall M is given by this. So we are now going to the structure of recall that M consists of all those E contained in X such that E intersection MF is a test collection of subsets, okay, to determine which of the subsets of X are in M. So the criteria is that M consists of all those E for which E intersection K belongs to MF for every K compact. Okay, so this is the definition of M. Now remember, see, this would consist of the whole of X. This would also consist of the empty set. Okay, that's clear. Whereas MF may not contain X. Okay, so just make that remark. Want to make that remark? For instance, it's very simple. If you work with the usual Lebesgue integration, then you see that if X is equal to R, now see what I wanted to say is that it's a remark. X Y, for example, if full of R with the Lebesgue closure, Q of R is infinite and hence R does not belong to that's just a remark. So it may differ on X, what X you choose. Okay. But you see that X has the property that suppose X is a subset that you are taking of, or R itself is a subset that you are taking for this. Take any compact subset of R which has certainly finite Lebesgue pressure, and you see that the intersection of these two is again that compact set which has a finite pressure. Therefore, that is immensely qualified to be in M. So you cannot make a statement that, so this is not necessarily. Okay, so this is detail. Now what we prove is this, we prove the major theorem, step 8. This is a sigma algebra containing all Borel sets. So it takes care of all the open sets. Now you are assured that all open sets in X are measurable. Okay, it belongs to the sigma algebra. So it's a measurable set, right? So that's the important part. So this is sufficiently huge collection of subsets which has the property that it is a sigma algebra, and so that you are comfortable in defining a measure on it. That's a point that we want to make. So this is essentially the sigma algebra that is determined by the non-negative linear functional that we have started with. Okay, so M is the sigma algebra induced by lambda. Remark. Induced by lambda. Okay, mu we have already defined, and consequently we will later show that mu becomes a measure. So we eventually prove that and for which on which lambda if This is essentially what we are. But in this step, we are only proving that this is a Sigma algebra and large enough, containing all Borel sets. What does it mean? You are assured that all open sets and all closed sets are measurable. Okay, that means the whole topology is smoothly integrated to the measure space. Okay, that is the advantage that you have. So let us prove this first. So what are the things that you have to prove here? One, X and empty set both are in M. Secondly, if A belongs to M, then A complement belongs to. Further, if obviously A union M, A union B, A intersection B, they are all okay. Or more generally, we have to show that M is closed under countable union and countable intersection. Countable intersection would follow from the fact that if A belongs to M, then A complement belongs to. Okay, so these are the things that we have to prove. So you see that the way to get script M from MF is through K. Okay, right. So we'll use that. So K is compact. If A belongs to M and then A complement so this is what we want. A belongs to M and A complement A belongs to M implies A complement belongs to M. Now let us write A complement intersection K is essentially K minus A intersection. Okay, which implies A complement K is the difference of two compact sets. Both because A intersection K is what? A intersection K is A, I cannot say it is compact. But A intersection K is certainly A is in yeah. So A intersection K is in MF. Difference of two both in MF. Therefore, so that implies A complement intersection K which implies A complement belongs to, we started with an A belonging here and then we prove that A complement. So that completes that part. The next part is we talk about the countable unit. So let AI claim A belongs to okay. Set B1 equal to A1 intersection K is any arbitrary compact set. Okay, so we fix the compact set K and K is any arbitrary compact set. Kept so set is equal. Then define Bn as An intersection K minus Pn minus for all values n equal to 2, 3, 6. Now, one can easily show that Bn is a disjoint sequence of members of M. Hence, by step 4, and the fact that A intersection A infinity, it follows So this is closed under countable union of what are called elements, or MF is closed under countable union, and therefore this follows. Therefore, it implies that's what we wanted to prove. We started with the assumption that this is so, and they are all elements of M, then their countable union is also an element of. Now you see everything is clear now. Okay. So it follows that the X belongs to M. Okay, because X intersection K is always in MF. Because every K is in MF. That's the reason. Secondly, for any A, its complement, any A in MF, any A in M, its complement is also in M. That's what we proved. And finally, we proved that A intersection, or if A is a countable union of elements of M, then it is also in M. Okay, so that's what proved. From this, by complementation, you can get that countable intersection of what is called elements of M is also in. Okay, so that you get straight away by complementation. And naturally, if X is in M, empty set is in, its complement is in M, therefore it's the empty set is the complement of X, and it is in. Therefore, now you see that M is equal. So that is the result that we have. Now, what remains to be said is this. It contains all boron sets. Let C be a closed set. Then C intersection K is compact for every compact K. Why? It's a closed set, K is a compact set, therefore C intersection K is also a compact set, and therefore it is in MF. And hence in MF. Therefore, C belongs to M. This is what we want. We want C intersection K belong to MF, so that assures that C is in. Okay. So all closed sets are in M. Therefore, their complements are in M. So, which implies all closed sets in X are in M, and hence all open sets now the Borel sets are generated from open sets by taking countable union and countable intersection. Okay, so Borel sets intersection of open sets and the sets obtained in this way. That means you take all what are called F sigmas and C deltas. Okay, now F sigma delta, F delta sigma, etc., etc. So this process is over and over again, and they all belong to M. Okay, therefore so that is the outcome. So you get a very nice sigma algebra containing all Borel sets. That means, you see, the Borel sets come out from the open sets in the topology on X. So all topologically significant sets are now measurable. This is the greatest advantage that you have. Therefore, we have arrived at the, the sigma algebra on which we can now set mu. And then you can show that this is indeed a countably additive set function satisfying all the required properties of to be a measure. Okay, and finally we put them together and show that lambda f is indeed equal to integral over x of f. I think today I will stop there and then take it up tomorrow most probably. Thank you very much.